Hello and welcome. This is World of Wastewater, and you're watching part 16 in a series going over a wastewater exam, which you can find a link to in the description below. If you're following along, these questions are numbers 76 through 80. Hit like and subscribe if you think your treatment plant is haunted, and let us know why in the comments. With that said, let's get started. Which influent characteristics would have the most adverse impact on a treatment plant? A. Low flow, a pH of 7, low TSS. B. Average flow, pH of 7, low BOD. C. Low flow, pH of 4, 0 DO. D. Average flow, pH of 7, 0 DO. The answer is C. Low flow, pH of 4, 0 DO. Influent characteristics are the physical and chemical properties of wastewater that enter a treatment plant. Although each of the choices in this question had at least one characteristic that will impact the treatment plant negatively, choice C has 3 negative characteristics, which makes it the correct answer. Let's analyze each one of these. The first negative characteristic was low flow. When the flow to a treatment plant is less than what it is optimally designed for, it will lengthen the detention time within the tanks or basins. For example, in a primary clarifier, a detention time longer than 2 or 3 hours can create septic conditions that produce foul odors, which no one wants. Next, a pH of 4 would be considered acidic and potentially harmful to the aeration system. For most treatment plants, a pH range of 6.5 to 8.5 is generally acceptable, and a pH of 7 to 8 is ideal. This is because the bacteria we want to keep alive and grow will die or fail to function properly outside of that pH range. For example, nitrifying bacteria do not perform well or grow if the pH is below 7. Lastly, the third influent characteristic, DO, or dissolved oxygen. If that's 0, that is not a good thing. DO is essential for the ability of facultative bacteria to break down organic matter efficiently and without producing odors. If your influent has 0 DO, it's going to be much more difficult to treat right off the bat, and will likely be producing worse than normal odors upon arriving at the plant. For those reasons, choice C is the correct answer. What is the temperature range for a digester to be considered thermophilic? A. 78 to 95 degrees Fahrenheit. B. 122 to 140 degrees Fahrenheit. C. 86 to 100 degrees Fahrenheit. D. 101 to 133 degrees Fahrenheit. The answer is B. 122 to 140 degrees Fahrenheit. A thermophilic digester is a kind of biodigester that operates at temperatures above 122 degrees Fahrenheit or 50 degrees Celsius and produces biogas. One advantage of having a thermophilic digester is that it ferments sludge roughly 6 to 10 times faster than a mesophilic digester, which operates at a lower temperature. Another advantage of digesting sludge at this higher temperature is that it will do a better job of destroying pathogenic bacteria, which is required if you want to produce Class A biosolids, which can be used as fertilizer based on current EPA guidelines for land application with no restrictions. With that said, a disadvantage of thermophilic digestion is that these digesters require more attention and resources. For this reason, most treatment plants prefer to use mesophilic digesters because they're easier to operate and maintain. A centrifugal pump uses 15.2 horsepower to deliver 800 gallons per minute against a head of 75 feet. How many kilowatts of power must be supplied to the motor to produce this amount of flow? A. 9.7 kilowatts. B. 11.3 kilowatts. C. 20.4 kilowatts. D. 17.2 kilowatts. The answer is B, 11.3 kilowatts. This is sort of a trick question because there are 2 correct ways to solve this, a short way and a long way. Let's start with the long way. We are going to use this power in kilowatts formula to achieve our answer. What makes this tricky is that we have converted our units to metric. The flow and the head in our question need to be converted to liters and meters, respectively. This formula, along with the corresponding conversion factors, should be found in the formula packet given during your exam. The first step is converting the flow of 800 gallons per minute to liters by multiplying it by the liter to gallon conversion factor of 3.785. We also need to convert our units from minutes to seconds, which we'll also do in this same step by dividing by 60 seconds per minute. This gives us an answer of 50.47 liters per second, which we'll plug in as the flow value for this equation. In the second step, we convert our feet of head into meters of head. We achieve this by multiplying 75 feet by the conversion factor of 0.305 meters to feet, giving us an answer of 22.88 meters, which we'll use as the head value in this equation. In step 3, we'll bring it all together. Let's take our flow of 50.47 liters per second and multiply it by the head of 22.88 meters and multiply that by 9.8, which is a constant value representing gravity. This gives us our answer in watts, which by dividing by 1,000 gives us kilowatts. So our answer is 11.3 kilowatts. Alright, so that was the long way of solving this problem. I wanted to show this way because it's important when working in wastewater to be able to convert between imperial and metric. The short version is just one step. We'll use the horsepower to kilowatts conversion factor that you can find in your exam formula packet. In this step, we take the 15.2 horsepower being used by the pump and multiply it by 0.746 kilowatts per horsepower conversion factor, yielding the same answer as before, 11.3 kilowatts. I want to note that you're more likely to encounter an electrical question on the higher level exams for your state. Water resource recovery facilities use an enormous amount of electricity, so looking at equipment through the lens of power consumption is an important area of concern. The more electricity your system consumes, the more expensive your overhead costs are for running the plant. A wastewater treatment plant has a rectangular aeration basin that is 30 feet long, 20 feet wide, and 25 feet deep. The flow to the aeration basin is 400 gallons per minute. What is the detention time of this aeration basin in hours? A, 5.2, B, 4.7, C, 3.1, or D, 7.9. The answer is B, 4.7 hours detention time. Detention time is an important concept in wastewater. How long water stays in the basins or tanks at your facility will alter how your processes function and will directly impact your plant's odors, biology, and effluent quality. This is why when your influent flow is too low or too high for an extended period of time, it can cause negative issues at your plant. We're going to use the detention time formula and the volume of a rectangle formula for this equation, along with the conversion factor of cubic feet to gallons. Although this information will be given to you for the exam, I would highly recommend that you have the conversion factor and formulas memorized, as they are simple yet essential for an operator. As a reminder, the more you have memorized before your exam, the more confident you'll be when taking the exam and the less time you'll spend on questions, which will help you overall. Now let's break down the math. For the first step, we'll use the volume of a rectangle formula to find the volume in cubic feet of the aeration basin. We do this by multiplying the length of 30 feet by the width of 20 feet and the height of 25 feet, giving us a value of 15,000 cubic feet. In the second step, we convert that volume in cubic feet to gallons by multiplying 15,000 cubic feet by 7.48 gallons per cubic foot, giving us a result of 112,200 gallons for the aeration basin volume. In the third step, we need to realize that in this question, we're being asked for the detention time in hours, so we must take our flow, which is given in gallons per minute, and convert that to gallons per hour. We achieve this by taking our flow of 400 gallons per minute and multiplying it by 60 minutes per hour, giving us a new flow value of 24,000 gallons per hour. Step 4 is our last step, where we plug in the volume value from step 2 and the flow value from step 3 into our detention time formula. This is 112,200 gallons divided by 24,000 gallons per hour, giving us our answer of 4.7 hours detention time. Before moving on, I want to stress that the units must be compatible. Detention time questions are fairly common to find on an exam. Don't let them trick you though, as they're deceptively simple. The exam might give you a flow and volume and make you think you can just plug it into the equation. Make sure you understand what units they're asking for in the final answer. Which aeration mode is most effective at reducing the impact of high organic influent loading? A. Plug flow, B. Extended aeration, C. Step feed, D. Dissolved air flotation.
The answer is C, step feed.
The aeration mode known as step feed allows the primary effluent to enter at 2 or more points along the length of the aeration basin. By introducing the primary effluent at multiple points, the plant can more quickly adjust to the increased organic loading and prevent the system from becoming overloaded. Another way to describe organic loading is by calling it food. When too much food enters an aeration basin at a single location, it will significantly lower the dissolved oxygen, which can create an environment that favors the growth of filamentous bacteria. By spreading out the concentration of food, the good bugs can more effectively perform their functions and continue to outcompete the filamentous bacteria. It's important to understand that even with a step feed aeration mode, the dissolved oxygen will take a dip due to the increase of food and biological activity taking place. But ultimately, the dissolved oxygen will recover more quickly than if the food was not distributed, like with a plug flow aeration mode. Another point worth mentioning is that the diagram I've displayed on the screen shows 4 locations that primary effluent is being distributed at inside the aeration basin, with each valve open 25% to show equal distribution. However, in real life, the amount of flow distributed to the aeration basin can vary from treatment plant to treatment plant. For example, it's not uncommon to have the flow tapered as it enters the basin, meaning you could have a 40, 30, 20, 10 split for primary effluent distribution. In any case, how open these valves are is going to change based on your treatment plant's specific needs. Being able to have this kind of flexibility makes the step feed aeration mode quite useful in activated sludge treatment systems. Hey, thanks for watching! If you enjoyed this video, then check out the others on this channel. If you want to help us keep making great content for operators, check out the description of the video. See you next time on World of Wastewater.